All right, all right, all right. We are back with Paul, Dr. Footleg Fretwell. Can I hear you?
Can you hear
Yes,
me? Can
yes,
you
I
see
can hear
me?
you. Lovely, fantastic. Well, there sits before me a man who needs no introduction, but I'm going to give him one anyway. Bestriding the Pi Wars conference like a colossus, Footleg has already spoken at pretty much half of our events so far. So today he's going to share his deep wisdom about building PCBs. I've been following this very closely myself. He's made some really interesting stuff over the last year or so, and I hope to just learn a little bit of his electronics wizardry. So with no further ado, I'm going to hand over to Footleg. If you've got questions, ask them in the chat or come on video.
Yeah, so this is very much an unscripted session. As I put all my time and energy into preparing my opening talk for yesterday, this is pretty much kind of live from my desk. Ask what you want, and I'll show you what you're interested in. So my journey into PCB design started with this Pi Wars robot from 2019. And if you heard my talk yesterday, you'll know that when I designed this, the electronics were a bit of a challenge in terms of fitting everything into the chassis, partly because of some of the design decisions I've made. So this is basically the electronics layout that I came up with. I decided to use, with my Raspberry Pi, the hyperpixel display from Pimeroni. And these touchscreen displays use, as it turns out, every single GPIO pin. So when I looked to see what pins were used so I could find some robot control hardware that was compatible with the remaining pins, I realized there were no remaining pins. And the only saving grace was that the software I2C bus, or I2C bus, was broken out by this board. So everything had to hook off that. And I had servos and DC motors to drive, as well as all of my sensors. So everything had to be I2C based. And I picked up one of these servo boards, breakout boards from Adafruit, which was an I2C pulse width modulated 16-channel chip, essentially, on a PCB. And I realized that as well as driving my servos off these channels, I could use the remaining channels to provide the pulse width modulation to the motor drivers. So the motor drivers aren't attached to the Pi, they're attached to these PWM outputs from the servo driver board. But I would be driving these ones just as pulse width modulated to control the amount of power going to the motor driver. Power basically then goes from the LiPo I was using directly to the motor drivers, so I was overvolting my motor slightly. But I used UBECs, these universal battery elimination circuits, to take the voltage down to a safe voltage for the electronics. The Pi was also run off a UBEC, although it's not shown on this one. It's not really shown on this diagram. This UBEC here, which is driving this power distribution board, is actually driving the Pi, although I didn't drive the Pi just through its I2C bus. These are going to the 5-volt and ground pins on the Pi. I then used a bit of Vero board to enable me to hook up multiple I2C devices, and I had 3 time of flight sensors, but they were connected via an I2C MUX device where you can toggle different channels to be active, because all of these sensors, when they boot up, have the same address. So that was how I solved that problem. And this extended then to have a bunch more I2C electronics on by the end of the thing. But you get the basic idea. So all of these breakout boards were going to sit on a piece of Perspex above the Pi, and the Pimeroni screen, which you see looking really neat on top of the robot, that was connected via a ribbon cable. But that ribbon cable, if you look carefully here, in order to get from the GPIO header here to the correct orientation to go into the hyperpixel screen, it actually had to be folded three layers thick. It had to go across, come back on itself, and then do the 45-degree fold. So that took up a ton of space in the case. And then above that, I kind of squeezed all of the electronics onto a second layer. And the idea was that this cartridge, which looks really neat in CAD, would slide into the back of the robot, and you'd be able to kind of take it out to fettle with it. And it would be kind of really easy to kind of show people how the internals worked and manage it. Great idea in principle, but once all of the wires were on, it got pretty congested, to say the least. Here you can see the pie's actually been kind of removed, and I've got the electronics kind of squashed in the back there. It was so packed inside this case that it took about 20 minutes to get this thing out. And there's the view looking in the front of the robot at the wires that kind of, once that everything was in place, all the wires got pushed forwards. So this absolute rat's nest was a real nightmare to deal with. I had further sensors that I added after I'd designed all of that. And Brian Corteil gave me one of his hedgehog boards, which again just kind of breaks out the I2C bus and power for it in these kind of 4 rows of pins. So they're connected horizontally across the lines. So you feed in your voltage, ground, and your clock and data line, and then you can plug a sensor onto each one and have up to another 5 sensors off there. So I had one of these floating around in the front of the robot as well. It worked for Pi Wars, but I thought we could do better here. And so I came up with the idea of, well, what if I tried to design a PCB that had all of those electronics on, and also dealt with that problem of the rotation of the header, of the ribbon cable header, so that I could plug this ribbon cable directly onto a header in the right place, and it would just be a straight kind of, as you would like a ribbon cable to be, a straight line path. So let's go to KiCAD. And for those of you who don't know KiCAD, I'm just going to create a new project here so that I can walk you through the basics. KiCAD is an open source PCB design program. It is the only one I've used. So I can't comment on how it compares with various commercial offerings, but it's I've found it to be fantastically featureful. This is the latest stable release. You'll see a lot of chat on Twitter of people playing with the 5.99 nightlies, which are the developer builds where a ton of new exciting features are being developed. But that makes your files incompatible with the stable release. So for now, for all of my serious projects, I'm sticking with the stable version 5.17 at the moment. So I've created a new project, and you can see I've got 2 files. I've got a schema file, which is my electronic diagram, and I've got a PCB layout. So your schema diagram, this is where you design your electronic circuit. So we're going to do something really simple, just for demo purposes. We want some power for our circuit. And the first time you open the symbols, it has to load all the libraries, but then once they're loaded, it's quick. So we'll just go for 5-volt power. So I can stick that on. And I also want ground, which is also in the power. So we've got power and ground. I want to put some power into my circuit, so I want a connector to attach it. So I go to the symbols, and I'm going to go for generic connectors, 1x2, and you can rotate them with the R key. So I'm going to have a power connector, which I now need to wire up. Rather inconveniently, my 5-volt I want to be pin 1, and my ground I want to be pin 2. Now, as long as wires don't intersect, that is not an electrical connection. It would be an electrical connection if I had joined on like that, you see there's now green dots. So those show I've made an electrical connection. Wires that cross over are not connected. And for my circuit, I want to just have an LED, just because I want to keep it really simple. There's a general LED symbol. And as you probably know, if you are playing with LEDs, they're not usually 5-volt devices. So we also want a resistor. Which is a passive, so it's just R. There we go. Now I'm not laying this out particularly neatly because I'm just trying to do it in a hurry, but I want my 5 volts to go to my resistor, to my LED, and then I want to wire it up to ground. So there we go, an electronic circuit. Now let's make a PCB. Now, obviously, you need to decide what components you're actually going to use. You can give these values. So I'll go for 330R for my resistor. And typically on a circuit, everything is numbered. Now, KiCAD does this automatically for you. So when I click on the assign footprints, it's asking me, do I want to keep existing annotations? I'm just going to go ahead and number everything because nothing's numbered yet. So when I click annotate, notice now everything's got numbers J1, R1, D1. And now it's loading up the footprint libraries because for my PCB, I need to know what kind of component shape am I going to have on my PCB. Okay, so my LED, I'm going to go for surface mount components. So I'm going to pick the LED SMD group. Now this is where my learning journey started really in detail, because what on earth did all this mean was my first question. There's lots of different sizes of surface mount components, from small but manageable for hand soldering down to kind of really almost impossible to hand solder because they're so tiny. And because I was learning, I went for, with some advice, the 805 hand solder footprint. The 805 devices are, in fact, we can look in the footprint viewer to see how big they are. So this is the footprint which will appear, and if we get the calipers out and measure it, you can see it's 3 millimeters long and about 1.5 millimeters wide. So it's small, but it's not unmanageably small. Now I've got comfortable with surface mount soldering, I'm actually typically going for the 503 size, which, as you can see, in fact, the dimensions are actually in the hand solder footprints. It's just under 1 by just over 1 millimeter, so a little bit smaller. People do hand solder the 402s. They're happy to do that. Very few people try and hand solder the 201s. In fact, if you kind of sneeze, then those components just vanish off your desk, never to be seen again, like motes of dust in the carpet. So we're going to go for an 805 because we're starting out. So I can just double click that, and you can see now my diode has a footprint associated with it. For my connector, I want to choose something to provide my power connector. So let's have a look. There's all sorts of choices here. We could go for a barrel jack. Let's go for everybody's favorite crimpable connector, the JST. And if you know JST connectors, that's a brand, not a connector type. The types are in these 2-letter codes. And a very common one for kind of power up to about 2 amps is the PH. But notice there's an absolute ton of PH as well. Now we're 2-pin, so GA 2-pin, and do we want it to be vertical or horizontal? Now, if you're not sure what your footprint's going to look like, again, the footprint viewer is really handy. Then when I select the footprint, you'll see what it's going to look like. So that's a through-hole footprint. That's a surface mount footprint. And there's a 3-pin version, 4-pin version. So we're going to go through whole 2-pin, which is that one. And finally, we've got a resistor. So resistor surface mount, and we'll go for an 805 again. Notice that there's metric and hand solder metric. They're just slight, although it doesn't help that they jump in scale here. Actually, this is slightly smaller. What you find with the hand solder ones is that when the resistor's on there, there's a little bit more empty pad either side of the resistor, so that you've got a little bit more space to get the soldering iron in to do the component. So, and you can see there's actually two sizes of hand solder. One slightly wider than the other. So depending on what you're comfortable with, pick one. So I've picked all my footprints. So now all of my components actually have a footprint associated with them. The next thing we need to do is export that as a net list. This is all of the information needed by the PCB layout part of KiCAD. And it just exports as a file. We'll just call it demo.net, save it in the project directory. So now we can go on to the PCB layout part of the program. Now the first thing you need for a PCB is an outline. And you can see there's a whole bunch of layers on the right hand side here. I'm going to start with the edge cuts. These are essentially the lines that will cut out, there'll be cutouts in your PCB. And we're just going to, why is my snap to grid not? There we go. I was just zoomed in too far. So I'm going to draw an outline. So my PCB now has an area for me to work on. And now I can import all of that information from my circuit from the net list. And you can see it's giving me a bunch of information about what changes it's going to apply. And as you'd probably expect, it's bringing in 3 new symbols. Click update PCB. And you'll see that I've got my components. And now you can kind of begin to see the scale that we're working at. So I've clearly made my PCB far too big for my components, but we can shrink that later. So my power connector, I'm going to put near the edge of my board, and I'm going to rotate it to be that way around. Now you can see that things are joined by lines. That's showing where the electrical connectivity needs to be. So decide how I want to lay these out. I'll rotate them so that they look nice and neat. And obviously it makes sense to put the pads that are connected together adjacent. So I want to rotate that to be that way around so that, and now things are crossed over. So that kind of doesn't make a lot of sense. So let's put the resistor above the diode. Now you can see my lines aren't crossing over. And now I can draw my PCB copper traces. So my ground is going to obviously connect to ground. Now I've chosen a very large kind of grid snapping size here just to get those layouts I normally work at 25 to kind of keep things neat. So my circuit's very simple, so there's not a lot to connect up. Now we've got an electrically complete circuit. Yeah, my power goes to my LED, which goes through my resistor back to ground. My PCB is way too big, so let's shrink it down to a sensible size. There we go, that looks a bit more sensible. Now the third part of KiCAD, which is a really nice feature, is it has an automatic 3D renderer. So I can actually look at how my PCB is going to look in the 3D viewer. And here you can see a 3D model of my PCB. There's nothing on the back except the through-hole component obviously goes through to the bottom layer. You can see where the copper traces are, and I've got through-hole components turned off at the moment in the options. If I turn them on, you can usually. So you get a nice 3D model. So hopefully that's kind of giving you a nice flavour of KiCAD PCB and how to design a PCB. So let's go back to look at my robot problem. My KiCAD PCB obviously had a lot more components. KiCAD has a really nice pi hat template, so you can import the template and you get the actual dimensions of a hat with the 4 corner holes and the GPIO header in the right position, all laid out for you, ready to go. And it has these kind of extra drawing markups showing you where the USB and RJ45 ports were for the Pi 3, which is the template's built around. So the question I kind of had to answer before I got this far was how do you go about designing a circuit for these breakout boards? And there is an immense learning resource here, which is the wonderful Adafruit and all of their open source ethos. So we were using a servo driver breakout board, and we need to understand how that circuit works. So here's the board, 16 channel, 12-bit. Now, when I used to buy Raspberry Pi hardware, what was on this board was just a mystery to me. Whereas now, whenever I see a board, I think, oh, I wonder what that chip is and what it does. Because of the amount of learning that this kind of project has taken me down. So let's have a look at this board. It's got a chip on it, and it actually tells us what the chip is in the title of the board. You can go and look that chip up on your favorite electronics suppliers, find the data sheet, and it will tell you all the technical information about it. It often will have an example, a typical used diagram in the data sheet. But even better than that is that Adafruit will have published all of the technical specifications in their tutorial. So let's start with the schema. So this should look familiar to you, having seen the KiCAD schema layout. You've got the electronic circuit, and in the case of this board, this chip has 6 address jumpers. So we need to understand how an address jumper works. Basically, if that pin is set high, then it will change a bit in the 8-bit address of the I2C bus for that chip. So there's 6 bits, which means that there's 2 to the power 6 possible addresses this can have. If the pin is low, then it won't set that bit. Now, in electronics, things aren't high or low if they're not connected to anything. So if this pin is just left unconnected, it's floating. It could be high, it could be low, or more likely and more problematically, it will flip between the two as random electronic noise passes through the ether from all of the electronics around your robot. So it needs to always be connected. So how do you connect it in a way that enables you to change its connection? What you do is you use the technique of a pull-up resistor. So here you can see pin 6 is connected to ground through a resistor, and there's an open solderable jumper connecting it to power to make it either 0 or 1. So if the jumper isn't soldered, then there's a 10k resistor pulling it down to ground. But if you put solder on the jumper, then that solder is a dead short, which means what you're doing is you've shorted V++ to ground through a 10k resistor. So the current flowing is minimal, and it pulls the voltage of that pin up to V++ or VCC, as the convention is. So each of those pins just has a resistor pulling it to ground and a jumper to optionally let you pull it up to. So I needed those on my board. I now understood how that part worked. There's a resistor on the OE pin, the output enable pin, again pulling it up, pulling it down to ground. So the chip is always enabled because the pin is held low. But if I connected this pin to VCC, it would pull it up in the same way that these pull-ups work. These are pull downs technically because they're pulling it down to ground. So you could actually disable the chip by pulling that to V++, and we'll come back to that in a minute in my design. And then we've got all of the 16 pulse width modulated outputs. They all go through a resistor to a 3-pin connector, and your 3-pin servo connector has 1 pin for the logic, which is connected to the chip, 1 pin to 5 volts, and 1 pin to ground. So everything you needed to understand about the circuit. But one more bit, there's reverse voltage protection. So they're using a MOSFET little circuit here to protect you from reverse polarity. And there's a big capacitor to let you kind of smooth the supply voltage to your servos if you're using big chunky servos. So lots of kind of useful stuff on the schema. So now we kind of understand how to design one of these. That enabled me to lay out the board. So let's have a look. Here's our IC, our pulse width modulated output. You can see I haven't yet connected up all of these pins. So these are little array packs of 4 resistors. So my so my resistors that are protecting my my pins go in here, 1 per pin, and there's a total of 16 on this board. But I'm using 2 of them, remember, for I'm using 2 outputs each for my motor drivers. So here's my motor driver chip. And if you look up the breakout board that I used for my motor drivers, which is another Adafruit product, then the schematic for that is on there as well. So there's kind of everything I needed to know to understand my breakout board circuit, and I just relayed it out on the board. Likewise, my rotated GPIO header, which had lots of traces going down, and the inputs and outputs for my servo power, motor power, and my 2 blocks. So I've started to kind of lay this board out here. I haven't yet put the address jumpers on, so let's have a look at a slightly later revision. So in this revision, I've now got the 2 motor drivers done. And notice that I've got these really thick copper traces because we're driving up to, these motor drivers can handle up to 3.6 amps. And so they need thick enough copper to take that current without the traces getting overheated. So a lot of work went into trying to design this to have enough copper thickness for these high current traces. And you'll see in the later design how I kind of further refined that. And notice that I've now got green traces as well as red. So the green ones are on the underside of the board and the red ones are on the top, because in order to get all of these GPIO pins mapped across, I needed to put some on the top and then some on the bottom. By the time I was finished, things had got pretty congested. But because you're learning one step at a time, you kind of pick up the flavor of how things work. And then if we jump back into KiCAD and I open up that actual project, you can turn all these layers on and off. So let's take off everything but the edge cuts. So here's the basic layout of our hat with its slot for the camera cable and its cutout for the display header. Each of our components has what's called a courtyard, that is the area that component physically takes up on the board. So you don't want these to overlap. So they're handy for kind of making sure you don't put things too close together. We have a copper layer. So here you can see all of the copper on the top of my board. And you'll notice now that my motor drivers are down much closer to where they need to be to keep these high current copper traces short. And I made them as fat as possible. And I can turn off the top copper, turn on the bottom copper, and you can see the layout of the underside of the board. The through holes go through the board, so they apply to both. And these dots are called vias, and they take a trace from the top of the board to the bottom. So if I turn on both layers, you can see that a trace can go from somewhere on the board. It can go underneath. It can go underneath some tracks, and it can pop back up through another via. So you keep routing your board until you have no more unconnected traces. So it looks immensely complicated, but actually, when you break it down, the principles are the same on that really simple board as they are on this really complex one. And now you can jump into the 3D viewer, and there we can see my final board layout with all the silk screen. Some nice artwork based on the robot, and you'll see that I started to put components on the back. We'll come back to them because I want to tell you a bit about the story of how everything went. So I got my first boards back. I was really pleased with them, but let's bear in mind I was really kind of learning from the ground up here. And just to get to this point, I had an immense amount of help from people on Twitter. If we look at my Twitter timeline from that period, you can see that way back in October 2019, I was putting things up for what I would call peer review. I would post a picture of where I'd got to. So this is taken from the KiCAD 3D viewer. And I'd say, what do people think about how I've done this? And I would get tons and tons of useful feedback from people. I did the same thing with the PCB layout. So I'd post these sort of pictures, and people would say kind of like, oh, I'd look out for these sort of electrical issues that you might not be aware of. And I learned an immense amount and was saved a huge amount of pain by using that approach. So the boards came back. I was really pleased with them. Then I measured up my components I'd bought against the footprints, and I realized that I had completely misunderstood some of these footprint terminologies. So you can see here, this is one of those resistor arrays, and this is the footprint it was designed to go on, and you can see the footprint is way, way bigger. So I've completely messed up on my footprint sizes for my resistor arrays. So I couldn't fit the components I bought on the board. So I looked for components of this size and found that they did exist, but they weren't very common. And as a result, I had to buy something like 100 of them, and it was going to cost about 30 quid to get the components. The boards had only cost me 20 quid to get made, including all the shipping. So it wasn't cost effective to go and buy 30 quid worth of components. There was going to be a revision to the board. But all was not lost, because by a happy coincidence, the width of these traces was actually the width of a surface mount 805 single resistor. These were my first photos of my attempts at surface mount soldering, which I found surprisingly easy. But notice my resistor array, instead of having a little IC on there, I've actually edge mounted 4 single resistors. And that enabled me to make my board functional. It wasn't pretty, but it enabled me to at least test the design and see whether things actually worked. Now, more problematic was this RN4, because this is, if you notice, it's got 5 pins each side. This was a type of a resistor array that actually has 8 resistors in. So it has 2 ground pins and 8 resistors. And so it enabled me to put all of those pull-ups or pull-downs to pull all of my pads down to ground. But I couldn't put resistors across because this wasn't 5 resistors, it was 8 resistors in a more complex package. But undeterred, you can see my surface edge mounted resistors all the way along the edge here, and another 4 there. But here I built this resistor hinge where each resistor is mounted vertically, and then I had bits of wire tagging them to simulate the shape of the package that should have gone on there. And then one of the resistors is going across, bridging across to the pad that it went to. So absolutely horrible looking bit of soldering, but it meant my board was completely functional. So I was able to get everything on the board, stick it on a Pi, and there's my power LED, prove the thing worked. So I was up and running and able to do all the testing of my design, which was great because it enabled me to debug any other problems on the board, and I was confident now I had a working design. I just had the wrong size pads. So naturally, what would you do? Get another batch of boards made, and you'll be up and running. But I'd learned so much that I had more ideas, and I thought of lots of improvements I could make to the board. So I started doing a kind of improvement to the design and seeing kind of, well, what else can I squeeze on before I get these boards made? And so version 2 was born. There's a bit of the testing of version 1, proving it worked with the Pi Moroni display. And then we came on to version 2 of the board. Version 2, there's a feature on these boards which when you're using the hyperpixel display, the I2C bus is no longer connected to the standard I2C pins on the Pi because it's the software bus broken out on 2 of the other pins on the GPIO. So what I did was I connected everything that's I2C up to these 2 jumpers, one for the clock and one for the data line, and then you could either bridge them in for the software bus, which connected them to a couple of the GPIO pins over here, or to the hardware bus, which connected them to the standard 2 pins on the Raspberry Pi. So if you want to use the software bus, you can switch the whole board over to the GPIO pins that are broken out as the software bus by the Pi Moroni board support. On the back of the board, there was a bit of room. And one thing that had occurred to me is that I was driving a lot of I2C devices potentially off this board on the 3.5 volt rail, and the Raspberry Pi 3.5 volt rail isn't rated for particularly good current. So I put on a separate 3.5 volt converter so that I had an onboard 3.5 volt supply providing me with a bunch of current to kind of put a lot more devices on. This also gave another great advantage. You can use the board now without a Raspberry Pi because its power needs are completely self-sufficient. So because everything's off I2C, you could plug a microcontroller into the I2C header, which is either this 5 volt header here for supplying 5 volts into the board or taking 5 volts off, or there's a 3.5 volt, but you'd need to provide 5 volts because everything else on the board is driven through that voltage linear regulator. I also thought, wouldn't it be great if you could tap into your battery voltage and read your LiPo voltage? So I found a little 1-channel ADC chip, managed to squeeze that and its associated components on. So now I've got voltage measurement over I2C. And the other thing, which was an idea I was really keen on, if you remember that output enable pin on the pulse width modulated chip. Problem with these chips is that they're hardware pulse width modulation, which means that if your code tells it to run a channel at a particular pulse width output, it'll do that and it will keep doing it until you either cut the power or tell the chip to do something different. That means that if you're running your motor drivers off these, or you're running powerful servos and your Raspberry Pi stops talking to your board, maybe your program crashed, maybe your Raspberry Pi browned out, something else went wrong, your hardware on your board is going to carry on driving your motors at whatever power they were set to when you last talked to it. And this is a safety concern for when you're starting to build robots that are kind of a bit meatier. So I'd had this idea raised with a discussion with Rob Kopinski, who's one of the MakeSpace members, who's an electrical engineer and has been a fantastic mentor to me throughout the lifetime of my PCB adventures. It's given me a huge amount of advice, which has saved me from making a lot of mistakes. And he talked about this idea of a watchdog, where you have a separate process which is needs to be kept alive. So if you don't keep on talking to it, then it turns off your board. And that's what this WDOG pin here is. That's the input for the watchdog. The other feature on the board, which, because the GPIO was completely occupied by the hyperpixel display on my robot, I had no spare GPIO pins to do anything with. And actually to do things like turn on and off the laser sight on my nerf firer, I actually used one of the pulse width modulated outputs that was spare just as a logic I/O. So I'd either turned it to 100% on or 100% off, or 0% on, to just act as a kind of logic switch. But now I was designing my own board, well, why not put on a 16 GPIO output? So lots more features. Here's the watchdog circuit. The way it works is that it keeps the enable pin of the pulse width modulated hardware chip active, keeps the chip active for just under 1 second when you toggle the watchdog. So you have to, the watchdog input has to be turned on and off for it to keep the hardware alive. So every second you have to have turned that, toggled the logic state of that input watchdog pin, otherwise all your motors stop. And that means that you just constantly in your loop, in your code, talk to the watchdog, say, keep alive. Here's a kind of toggle high, toggle low. And that way, if anything goes wrong with your robot and you stop talking to it, all your motors are turned off. And that was the kind of idea of this watchdog. So let's jump forwards because I've got a few more things and we're getting close to the top of the hour. The final design I came up with, I decided to go for a bit more branding. So I've kind of come up with a Footleg Robotics logo, and I called the board Sentinel, came up with a Sentinel logo because of this watchdog feature. So that's the back of the board. There's the front of the board. There's the actual physical thing soldered up. That's the back. And here's a fully soldered populated board. So this was the first full Sentinel board in existence. And you can see I've soldered the hardware I2C bus on this one. I've put now a JST-PH connector for extending my I2C bus. So I've got a nice neat plug-on polarity kind of controlled. And then this one over here is a higher current capable JST-EH connector, which will give in the full 3 amps that the Pi 4 might need when you're driving the board. And I made a batch of 10 of them. Actually only 8 in reality, because one of them I messed up the soldering so badly of a chip that without the rework station at MakeSpace, which I've not been able to get to due to all the lockdown shenanigans we're going through, that board's kind of sat on the shelf waiting for me to be able to desolder that chip because it's out of position and I can't easily get it off. And I didn't have quite enough components to do the 9th board. So there's 8 in existence. And that hit the next problem. I'm thinking, right, now I've made 8 boards. How am I going to test them all? I don't want to solder. I don't want to solder all the headers on. That's a ton of extra work. And when other people get these boards, they might not want all the headers on. You only want the headers on that you're going to use. So I came up with this idea of a jig. So these things are called pogo pins. They're little spring-mounted pins. And I 3D printed a block to put them in. I've got 4 LEDs on the top, plus a little surface mount LED to show that the power's connected, and resistors to protect the LEDs. And this one fits on a servo header. So I could show you the physical thing, but it won't be clear on my webcam. As the idea is that you hold that on the servo pins when there isn't a header on, and you can run a test script and watch the LEDs flick on and off to show that all of those servo channels are working. So you can test all of the hardware on all of the boards, save an immense amount of work, because manually trying to test all of these with a multimeter was just a nightmare. But I can just plug that on, run the test script, and in less than a second see that all 4 of those, I've got no dry joints, everything's working as expected. I've also got my 16 GPIO input outputs, plus I've got 5-volt power and ground here, so I needed a jig for them. And you don't need to make a PCB for everything in your life. For this, I just got a bit of Vero board and just used a craft knife to cut the tracks, soldered on my LEDs, soldered the resistors onto the legs of the LEDs. You can see I kind of cut them into a hoop, held it all in place with blue tack, soldered it all up, and that plugs straight onto this area of the board, and I can run a test script and test that all 16 of my IOs, my digital IOs, work. And I can test the motor drivers through the terminal blocks. So building the kind of test rigs was a kind of really important next step in starting to think about kind of, well, if I'm going to produce these in any quantity, how do I make sure they work without having to solder on hundreds and hundreds of headers? If I got these boards made, and I've not looked into getting boards made yet myself. I've had the PCBs made, but I haven't had the assembly done. I've hand soldered all of these. Having hand soldered 8 of these, I don't want to go through that again. Not because it's difficult, but because it gets really laborious and time consuming. I think I spent 2 solid days of a weekend soldering up that batch of 8 boards. So I'm just going to jump back to my Twitter timeline, because this is how I kind of keep track of what I'm doing, get input from people, learn what's going on. A bit of Twitter search syntax, if you don't know it. If you do from : and someone's username, then you only get results from that person's posts. So I've just looked up everything that I posted, hashtagged PCB, sorted by latest, and I can flick through my timeline and see the whole evolution of my boards, my first soldering. There's the resistor henge, a little bit clearer picture than the one that I showed you that I put on Twitter. Videos of things in action as I was learning the ropes. There's when I had the first batch of Watchdog boards made, I made a bit of a cock up. I got something wrong in my circuit. My Watchdog didn't work. So, not to be unfazed, I tagged a line across. I removed a component, bridged across. There's a bit of wire you can't quite see there, bridging between 2 pads where I'd removed a capacitor that shouldn't have been there. And I managed to get the circuit working, having kind of mocked it up on breadboard to see what I'd done wrong. I'd highly recommend breadboarding your circuits before you get your PCBs made. I didn't know how to do that when I got these made, because the chips I needed to use were surface mount. But I've since discovered that there's readily available PCBs to surface mount, solder any chip onto, that then lets you plug them onto a breadboard. And so I bought some of those off someone on eBay and soldered one of these chips on, was able to breadboard the circuit, discovered what I'd done wrong. This was my first iteration 1.1 board. Before I'd come up with the Sentinel grinding. It was the first one with the Watchdog circuit on, and with this bodge wire I was able to get it working, learn what I'd done wrong, and the third iteration of the boards are the ones that you saw in the kind of batch manufacturing. So here you can see that early Watchdog board in action. And there you can see on the breadboard the test chip where I was testing my Watchdog circuit on one of these boards I was talking about. So I'm going to turn off the screen share just so that my webcam goes back to full screen. And I can show you the real thing. So here's the robot chassis prototype I was producing for Pi-Wars at home this year. Although regretfully, I've had to drop out of Pi-Wars at home this year because the process of homeschooling, lockdown, the fact I've moved house in the last couple of months, have all conspired to just eat up too much time. So I'm not yet at the state of getting the PCB to bring the circuit, which I'm prototyping here, forwards in time for Pi Wars. So regretfully, Danny and I have decided to kind of admit defeat at this point rather than killing ourselves with burnout, and hopefully get the robot built and working properly, but kind of do it at a sustainable pace. Here's one of the ready to kind of be treated as a production sample, fully tested board without the main headers on. So I've put on the kind of the main components, but it's kind of like got the through hole, all of the through hole headers the right way up. All the through hole headers are not soldered on, so it's kind of as you'd get a board if you bought a board. And no, I haven't yet set up a Tindy store, because the software development for the board, all the libraries, is a really important part of a product, and I'm still working on those. I also came up with the idea of improving my I2C breakout. So this is my I2C breakout board, and you feed the I2C in at one end with a JST connector, which would plug onto the JST connector on the Sentinel board, and then you can plug as many sensors on as you want. So here's one that would plug into one of my time of flight sensors. Here's a lead JST to quick lead, so I've plugged in an OLED display that's got a quick connector, and you can see how that extends. You'll notice there's also some 5-pin sockets on there. The 5-pin ones mean that you can also feed in 4 GPIO logic inputs, and they are connected to the enable pin on the 5. So if you know all of the Pimeroni breakout garden type boards, some of those have output enable pins on. So with that, you'd be able to add your digital I/O to turn on your time of flight sensors one at a time, set their I2C address in software to a different address than the default, and then hopefully run multiple of them on one I2C bus and do away with the multiplexer, be able to talk to them all much more efficiently. There's the jigs, which I was talking about. So this is the one that plugs onto the GPIO 16-way, 16 LEDs on the top. So you just hold it on there, run the test script, and you can check that all 16 of them are working properly as it cycles through. And what else have I got to show? I should probably just very briefly talk about power. So on my board, I use these Hobbywing UBECs. So there's my battery connector, plug my LiPo on there. This one you can see the wires snapped off, but that would have been soldered on there. That gives me 5 volts out into my connector that plugs onto my Sentinel hat. So everything's powered through that. I'd like to actually have my own power built into some of my circuits, and so that led me down the next rabbit hole, which was to try and design my own PCBs for power management. So this was my first test board, and it has the LiPo connector built in. It had a polyfuse, although this one I've just shorted the pins so there's no fuse, because I discovered that the polyfuses I'd used had their own problems. But it's much more compact than your typical. It's got a heatsink on the bottom because it got way too hot. The goal here was to be able to put up to 4 amps constant load, because most of the UVECs seem to either top out at 3, or they claim that they can do much more, but believe me, they get way too hot to be usable. So I'm on version 2 of that, which is the board's just arrived this week. So here's the first one. I've just soldered the first chip on onto its ground pad, and I'm just starting to kind of put that together. It's slightly bigger. What I can show you is how it would look in practice, because I've been using the 3D model that KiCAD generates to generate a PLA prototype, so I can test the placement of components for fit on the Pi. So on a Pi 3, and it's printed in 2 slices just so that I didn't have to put supports in to print the underside and the top. So I printed them in 2 halves and sandwiches together. So it slots onto the Pi 3, and now the heatsink is on the top and all the components are on the bottom, and I'm hoping that that will enable it to deal with the heat dissipation. I'm going to stop talking there and see if there are any questions.
Yeah,
because
I'm up against time, unfortunately.
Yeah.
So that has been absolutely fascinating. I think we've got time for one question, if there is one, but you have to type it out super fast because Rishan is on in like 2 minutes. Does anyone have a question? One question. If not, that's great because it's time for us to swap over. So thank you very much indeed for that. I've seen some of that before, but nothing like all of it. So that was a really good whistle-stop tour of the stuff that I've been really interested to see you working on. And I look forward to watching it back on YouTube and going through and seeing, trying to understand how KiCAD actually works this time, which is something that I've failed to do many times before. So maybe this will be the one. Anyway, thank you very much for everything.
If you have questions, I'm Dr. Footleg on Twitter. Always happy to chat on there. So do reach out to me, and yeah, continue learning, and I'll continue learning and sharing.
That's a fantastic message to finish on. Thank you very much indeed. I'm going to take a break for 1 minute, and then I will be back to introduce our final session from Rishan Sharma.
I hope you've enjoyed this remastered version of my live talk from the Pi Wars virtual conference. Unfortunately, the original live recording was so laggy that most of the visuals that I was talking about were completely out of sync or missing, with huge amounts of skipped content. So I have remastered this version and done all of the visuals again to go with the original audio. This has been about 18 hours of work in the editor. So I hope you appreciate the talk and found it useful. I have a Ko-fi page if you would like to show appreciation and encourage me to do further talks like this. There is also my Ko-fi page is the place where you can find links to all my other various YouTube content, which is largely spread across other organisations' YouTube accounts, as I do talks for STEM organisations and my local makerspace, Cambridge Makerspace. So all of that content is linked in my feed on the Ko-fi page. So if you're interested in more of my content, that's probably the best place to go to find everything that I do. Thank you to the Pi Wars conference organisers. It was a fantastic event, a real privilege to be part of, and we look forward to more, hopefully in-person events in the future.